Hey, welcome to Coffee Compiler Club. Here today to talk about compilers in theory. Well, there's a lot of other stuff going around. Language runtimes, language designs, type theory, anything, everything to do with language implementations and execution. Everyone's been recorded. We show up on YouTube in a couple hours. Um, no set agenda. That's the end of my normal starting spiel. Uh, let's see here. I'll mention that my wife's knee surgery is recovery is progressing. It's not fast, but it's progressing. So it's a move in the correct direction. Um, and then Zhiganov?
Evgeny, so I wanted to present today C compiler I've been working on. Firstly, I would like to apologize because I promised to present like 2 months ago and only show up now. But I have an excuse. I have been working on the compiler. And now I will try to share my screen. Can I do so? No?
In just a second, you can.
In English, his name is Eugene, so it's easier.
Eugene. Oh, that's much easier for me to say.
Yeah.
I do try to make the names sound how they're supposed to, but I don't always get it right. Fine. You should be able to share now.
So, can you see the slides?
I can.
Basically, I was not sure. I was not sure how to, what the format should be, so I prepared some slides, but then feel free to interrupt me and I will go to the code and whatever the question is then. And that's my agenda for today. Firstly, I would like to talk about what I've been doing and why I've been doing the compiler, then about the architecture for the most part, and what's next and what's my conclusions about all this process. And so, what? Basically, I've been, for the last 5 years, I've been working on independent C compiler for C17 standard, C23 standard, and also some GCC extensions. And quite a few of them, so it really compiles actual real-world software. And I have some necessary optimizations, debug information support, generate multiple assembly syntax variants, and the compiler is quite scoped, I would say. It's really like classical C compiler, integrates with external assembler, standard library, linker. Here's a typical setup on the slide. Works for BSD systems, for Linux, and 2 different assemblers. And basically, these are the systems I support at the moment. So this is what. And now the proofs, because I feel it's very important to actually tell you why I am now wasting your time here or I am not wasting your time. So how do I validate and how do I make sure that this compiler is actually a C compiler? Firstly, of course, I have my own test suite, which is quite large. It's, I think, even more now, 140,000 lines of code of just tests I run of my own writing. Then, of course, I bootstrap my compiler firstly bit identically on all supported platforms. That means that it basically supports reproducible builds. And also a portable bootstrap where the compiler bootstraps itself, the standard library, binary utils, libatomic, and also could bootstrap libgcc by compiling GCC version 4. And again, here I just make sure that the compiler actually is self-sustaining, so to say. And now, more interesting things, there are third-party test suites, basically GCC Torture test suite, which is used for GCC testing. I believe my results are quite good on it, so it's like out of 3,000 something, 600, only 450 tests fail, and those are mostly GCC specifics. I also do fuzzing, 20,000 cases per nightly run typically nowadays, and compare the fuzzing results against GCC. And finally, the most important thing for compiler validation, I actually compile the real-world actual practical software, like about 80 different projects, including GNU, binary utils, core utils, Nginx, OpenSSL, Python, quite a lot of different projects. And I believe this, especially this particular part, enables me to actually be confident in what I've been doing with the compiler.
How big how many lines of code in your compiler?
How big is what exactly? Source code lines or what?
Yeah, source code lines.
The compiler itself is about 150,000 lines of code. And there are also about 150 lines of tests of my own test suite.
Yeah,
so
the compiler itself, but yeah, okay.
So in total, the repository is about 300,000 lines of code.
Cool.
And it's like 5 years of development. And this is my recommendation. So basically, hopefully by now, I at least have convinced that it's not like total waste of time. And I will move on to the motivation of why I've been doing this.
It's not a toy for sure.
Who's funding? Are you self-funded? You just doing this in your spare time?
It's just my spare time. It's my hobby.
Cool. Okay.
It's not a hobby for sure.
I mean, I enjoy it, so it's hobby. I am not paid for it. I just do it in the evenings and weekends. But the why motivation, basically whatever is written on the slide, is just retrofitting motivation to the existing project. Because again, I am doing this exactly because I just enjoy writing the compiler, and that's my primary motivation. Of course, I have some problems with existing state of the art. Firstly, because major compilers for C are C++ only, like GCC, Clang, and it's not pure in my view. And there are smaller compilers, of course, but they are often, in my view, insufficient in scope, pipeline, or they are outdated. Also this compiler, I'm working on this myself with no collaborators, and so I kind of can iterate fast, and I can have some vision, which I believe I wouldn't be able to have if I was collaborating with anybody. But this is purely retrofit of some motivation, and my primary motivation is just because I enjoy writing the compiler. And now I'm finally moving on to the interesting part, perhaps, the architecture. Firstly, as mentioned, the compiler itself is very traditional in its structure. Sequential pipeline, forking, there is nothing in particular architecturally. But I will move on to the intermediate representation soon. But before that, I would also like to mention parsing, because for C, parsing is actually a funny issue. There are some quite famous problems, which I mentioned here on the slide. Of course, because firstly, the parser is not really context independent, and you actually should keep track of symbol types and some context when you are parsing. Otherwise, you cannot even distinguish like this very simple point, whether it's a pointer or it's multiplication, you cannot know until you know whether T is a type def or some variable. So in parser, you actually need to keep track of this. And secondly, of course, the most complex part of C parsing, I believe, is declaration syntax, because you are never sure what you're looking at until you have finished parsing the whole declaration. So with all these nested pointers and array syntax, there is some, of course, internal logic to this, as far as I learned by reading the standard, but it's I think it's historically more appropriate than. But these are problems with the parser. But then the intermediate representations, which I believe is the most interesting thing. The compiler has 4 different IRs sequentially, starting from stack-based intermediate representation, which is the most high level, through the SSA, which corresponds to the stack-based representation, but in different shape. Then there's linear tree address, which is already the target architecture level. And currently, the 4th one I'm working on now, and also that's partially the reason why I postponed this presentation a bit. I'm working now on SSA representation for the target level for x86. And I will discuss in more details now each of them. And the compiler itself also supports like JSON exports for all intermediate representations. So you can actually export all of them and inspect. And starting from the stack IR, here as an example. I would immediately like to mention that this part on the right is a bit kind of imagined, because as I mentioned, the compiler explores JSONs, and JSON is the primary representation which I work with. So whatever is on the right is just more like syntactic sugar, which I written down for your comprehension to fit it on the slide. But basically, it should be very, very familiar, so to say. It very straightforwardly compiles the C code into a stack-based machine. Perhaps could be even similar to Java bytecode.
Right.
But and basically the idea for StackIR, first it's complete abstraction for the target architecture. So if I go back here, it abstracts everything, including type definitions, data, function definitions, function ABI, and the compiler translator basically targets this thing, and it has no concern about whatever is architecture below. The StackIR provides some APIs to do things like size off and others, but overall it's just completely insulating anything for the translator of abstract syntax tree. Secondly, currently the stack is virtual, so it can contain mixed size operands and has no structure in control flow. And finally, perhaps the difference between this and, for instance, Java, I do not do any verification of this, so to say, StackIR bytecode. It's purely internal, so I kind of just trust it. It's not like something external. I can print it, but I do not consume it in the compiler. And firstly, the current rational, it's easy target for translating. So the translator layer of the compiler is quite simplistic. It does not do any optimizations itself at all. It just produces this stack machine code. And secondly, again, because it kind of insulates everything about the target architecture and provides APIs to get any details necessary, but the compiler should not know much apart from that. But that's not the initial rationale, actually. The initial rationale, because initially my compiler was producing threaded code for C. And the first version produced something like this. It was like actual assembly which it produced, and it was compiling and running it. And it was able to bootstrap itself. Basically, there was some preamble for each function where it stored the arguments into the stack. It set up the state it needs for this threaded machine, and it just started executing. And each of these routines actually had a definition in the runtime library which implemented this particular opcode. And I will say that it worked. It produced horrible code of horrible quality, but the code was functioning, which was a bit surprising to me because, again, it's not typical architecture for C, but rather for Forth or something, but
right.
It worked even for C.
I wouldn't, last time I saw this was Forth. I'd not seen this done for C. Yeah, fine.
Yes, because initially I started development, I was just, I didn't even want to produce C compiler. I was just doing some experiments with stack-based IR and coding something. And then I decided to integrate it with System 5 ABI. I studied the ABI, and I understood that basically if I do the integration, I am halfway through compilation pipeline for C.
Right.
Even though it was not halfway the effort, but this basically was the first version. But of course, immediately after I implemented this, I wanted something better. So the SSA IR, this architecture, I inspired a bit actually from your work, but it's more constrained. I called it puddles of nodes.
All right. I'm not sure to be honored or not.
It's not true sea of nodes. What I do, I preserve control flow graph structure with basic blocks, but within each basic blocks, I relax everything besides control flow in the basic block. Like I have like control and side effect, which is sequence structure within block, and everything else just flows within the block. So it's kind of, it's not a sea, it's a puddle, so to say.
Gotcha.
And I actually believe this is quite reasonable architecture for a C compiler, because for C it's very natural. The standard specifies that many things have undefined behavior with respect to sequencing, especially within an expression. So it's very natural to translate C like this, where you have strict control flow, strict flow of the instructions within the basic blocks, but then everything else is just flows somehow. And also,
you
in
have
my
a
opinion,
DAG within a block.
hmm?
You have a DAG within the block. Each block is a DAG of instructions directed to cyclic graph.
Yes, basically, yes. It's each block is a graph. Instructions do belong to the block, but they mostly float within this block. Of course, there is, as I said, there is this control flow backbone, which is also source for like side effects. But the rest is kind of floating. And also, I believe this is a good kind of middle ground, because I did not quite like LLVMIR, as it's too linear. And at the same time, actually, I did my master's thesis working on G1 garbage collector at University of Linz in collaboration with Oracle Labs, and they looked a bit at hotspot. And I will admit that full complete sea of nodes was always kind of a bit confusing to me as a developer. So I arrived at this architecture kind of trying to synthesize something which would allow me to be more confident. It's kind of a bit easier to reason about, in my view, at least for me in particular. But at the same time, preserve some flexibility.
More presentations on how sea of nodes viewed and think about and deal with that aren't widely viewed on public. They're available, but they're not. I don't know that a lot of folks have seen them. And that might help you understand what the hell I'm doing. But that's an entirely different talk. You should keep going here.
I mean,
we can go there. And if you're not, don't worry about it.
I mean, I think I looked at some of your materials. Again, to me, the most complex part is actually reasoning about debugging something. Because with this one, I am more confident when I'm debugging my compiler bugs. It's kind of more comprehensible to me. But it's my personal perception.
Sure. I've debugged sea of nodes for 20, 30 years, so I'm very comfortable with it. I know what the hell I'm doing. And I do a bunch of things with it that I don't see other people who were messing first with sea of nodes do, and then after I explain how the debugging goes, they get it. So there's a thing to talk about there too. That's, again, not your talk, so you should do your talk. And we'll come back around, because I'd love to share debugging tricks here. That would be fun.
Okay, then I will continue. So, and the idea that at the abstraction level, this IR shares the core abstraction with stack-based IR in terms of the semantics it presents. Yeah. So the shape is different, so more friendly to the optimizations, but at semantics level, it's still very high level. That was my kind of deliberate decision. And as I mentioned, there are some pros to this. Firstly, it's, I think, quite natural for C as it's defined. It's, again, easy to operate. It keeps control flow graph, and I still get some optimizations for free. That code elimination for free, and I'm a bit flexible in scheduling the thing. But the main cons, as I said, it's very high level. At this representation in my compiler, so with these presentations, there are limited opportunities for actually low-level particular optimizations. So the optimization pipeline I currently have, it's mostly focused on scalar complex numbers. There are some aggregate optimizations. Currently, I do not do comprehensive alias escape analysis. I do some when I lift memory to registers, do tail call optimization and inlining. But it's very ad hoc at the moment. And there are some optimization passes listed in the slide which I do, which should be quite...
should cover a lot of good ground.
Reasonable ones. But again, here I would like to mention that, for instance, I have this global value numbering, loop invariant code motion, but at the same time, with the level of abstraction in the this IR I have, it's very hard to do this reasonably. If I, for instance, do some loop invariant code motions too eagerly, I just mess up with creating too much cross-block dependencies, and my register allocator is not good enough to handle this at the moment. And I will address a bit later how I'm currently working on improving this. But at the moment, as I said, these other optimizations have. It's a bit too high level for very sensitive, target architecture sensitive optimizations. But That's what it is now. And it's already, I think, produces relatively good code. For the backend as it is now, I have instruction selector, which transforms this high-level SSA into a tree address code, linear one. This tree address code is already, it's basically x86 opcodes, a subset of them which I use, but with a limited number of virtual registers, and also some special instructions for like virtual register management, ABI management, and such. But overall, most of the ABI has already been lowered at this point by the instruction selector. So this is already very, very close to what actual machine is doing, apart from these virtual registers. And
what is vreg link?
It's basically like move, but more polymorphic. Like, because virtual registers can have different types, it can be general purpose register, it can be floating point SSC, it can be spill space, and link just, it knows these types and it will produce the right instruction for them when it's translated down. And also it produces hints for the register allocator that these, for instance, two virtual registers can be co-located.
Right.
So it's like a smart move, so to say.
Yeah, I have the same operation running around in my allocators. I just didn't get a different name. It's fine.
And so basically, this works, and this already worked for like 2 years. I've implemented this 2 years back, and it's kind of fine and produces somewhat reasonable code. But firstly, the pros, it's very easy to comprehend, debug, and generate. It's not bothering me much. But at the same time, I cannot do much optimizations for this. And because it's very linear and because of how I designed it, it's rather hard to do efficient register allocation. And these are the main limitations of this form at the moment.
I have an open source available register allocator in my simple project. It's written in Java, but you could port it to C if you were just interested in a graph coloring register allocator. It's very similar to whatever setup you have going on here.
I will talk. Just a few slides later, I have some material of what I'm doing next. So I will. Basically, yes. But at the moment, that's what it is. It works somehow, but I'm not entirely satisfied with the quality of the code it produces. And the last step before actually producing assembly is what I call devisualization. It's register allocation, spilling, and all these things necessary to remove these virtual instructions and actually produce actual x86 code.
Right.
So this is rather straightforward. I support, this actually allows me to support multiple dialects. I currently generate, like, for GNU, assembly, 2 dialects, and also YASM. And now the problems which I already mentioned. These backend problems is, firstly, I destruct the data flow information. It's not preserved properly, even though it exists on SSL level. I missed, therefore, I miss opportunities for optimization. I miss register allocate. It can be implemented in a good way, but at the moment I don't have, and even some debug information is less precise than it could have been. So, what's my solution? What's actually I'm working on now at the moment in progress thing? I decided to construct another SSA from this tree address code.
Okay, so when I do my compilers, I just keep the same SSA all the way through to the back end, and I flip from some idealized node to hardware instructions, and I add the registers to the thing, but it's still SSA, the same SSA all the way through. And then, so when I'm out the back end and I'm staring at a pile of 3 address ops kinds of things, all in basic blocks in order, it's still also SSA.
I mean, for me, it's
bytecode. I mean, print out the bits for the.
I mean, for me, it's also kind of a matter of how I evolve the compiler, because, as I said, I do it in my spare time, and I need to do this development in like some reasonable chunks so that I have some results running. So I firstly implemented this very early threaded code generator. Then I put in SSA after it, implemented this virtual assembly. now I'm working on another SSA, so it's kind of, so to say, evolution of what I do, and I didn't really want to do everything at once, just to keep it manageable. So the idea is that I reconstruct SSA, another SSA from this tree address code. Now it's already totally ordered, it's linear, it's basically specific to the x86, although the container should be more generic. What I do, I review these read modify writes, implicit parameters. I also review flags, but at the moment I do not use them properly for code generation. And the ABI has already been addressed by instruction selector, so this SSA is not concerned by ABI. It's completely transparent to it. And at the moment, what I have implemented it during the last month construction from this virtual assembly, basic transformations, basic copy elimination, some file elimination, critical edge splitting, and round trip destruction back into the virtual assembly with debug information. And this already works and validated on my complete pipeline of my validation, which I presented earlier. So this is again an example. This example is again a bit imagined in terms of syntax, because I work with JSONs, but that's how it looks for some quite nasty, I would say, instructions of x86, basically division, where I pull everything into explicit form. So division gets 3 operands, the 2 for dividend, whatever I divide, and the 1 for whatever I divide with, basically. And also the flags are modeled here, but at the moment I do not use them. There are some requirements attached, and each instruction again can produce actually multiple registers, multiple values, and that's the design I decided to implement to actually model the x86 reasonably in SSA form. I think this one I already mentioned, so that's what I have at the moment working already. From virtual tree address code into target SSA, I do construction, I do some very basic transformations that are necessary, and then I destruct back into virtual tree address code and still do the register allocation and the rest of the pipeline as it was before. So currently it's mostly testing how the construction, destruction, and these basic optimizations work. That's what I achieved now, and what I plan to do, of course, I plan to implement proper register allocation based on this SSA, probably kernel register allocator or something with live range splitting, so that it's more sophisticated. Of course, I will implement spilling on SSA level so that I can produce already this physical assembly without virtual registers. That's my goal in my implementation currently, what I'm working on. And challenges, of course, what I actually faced when implementing C compiler. First, the standard itself is not sufficient at all. You first face standard, you can implement the standard, and then ultimately your compiler will be useless because you have the ABI, thread local storage, dwarf, all this, some POSIX stuff, GCC extensions, and you actually have to implement quite a lot of them to get even the most basic code running. There are very few projects which actually are C compliant in strict sense. Most rely on GCC extensions in one or the other way. And secondly, of course, even if the standard forbids some behavior, people still do rely on it because GCC implements it. And so, as I would say, you implement the standard and then you implement even more and much more before you get something running. And actually, even the standard library, if you don't really want to implement standard library itself, you have to deal with existing glibc or muscle, and they still have some problems of their own to integrate with. And of course, with C, especially if you're testing against a lot of such code, you can never be sure what are you looking at. If it's your compiler bug, if it's the backend, the software you're compiling, because it assumes something about GCC and you are not GCC, and then I'm not even sure whether it's my bug or not, so I have to fix it. But
and came through in the Java land as well. Everyone assumed the first implementation of Java was the implementation, and they wrote non-compliant code. And then Hotspot came along, compiled things, and suddenly things broke. And now is it the spec wrong? Is the client, bug, or is it a compiler bug? Right.
Basically. And I mean, in my case, again, I try to handle as much GCC compatibility as I can, just so that I can actually claim that I compiled real code.
Yeah.
But I wanted to give some examples actually of this is glibc, excerpt of glibc standard library, what they actually do. They try to accommodate for non-GCC, non-client compilers by just suppressing the attributes at all. And then they still use attributes in for epoll, for instance, for some structures, defining some structure as packed. So even though my compiler supports the attribute packed and supports the syntax, the glibc assumes that my compiler is no GCC and therefore it doesn't support it, and it breaks the ABI basically by removing this packed attribute, even though the library was compiled with it. So I have to actually make some accommodations and some hacks just to work around whatever they assume about me, so to say.
Go claim that you're GCC somewhere.
It's not really. I mean, because if you claim that you're GCC, then they start doing even crazier things, and you have to actually implement all this GCC compatibility. I implement quite a lot for practical software, like for user space software, but in glibc, it's even crazier, I would say. So I still have to work a bit to actually get to the point where I can claim that I am GCC, because they actually assume a lot. So for now, I have a bit of like workarounds for this, but it's not a big problem. But sometimes you have to debug this, and you figure out that your ABI is broken because they overridden some attribute for some structure, and it's not what you would like to do. And of course, developer assumptions. I have shown all these validations, which I have like 80 projects, and it was all running and good. And suddenly I get a bug report with the code on the left, which developer tried to compile with my compiler, and it failed. And it's kind of so simple, but I have never kind of thought about this. But the point is that C standard forbids this kind of code, and it almost does not appear anywhere, but people still will try to do crazy things. And as long as GCC compiles it, they get away with it, and then tell me that it's my bug. So.
Yeah. In a sense, it is.
It is because
the spec is intersection of GCC and Clang, or the union of GCC and Clang.
Yes. So actually, I fixed this, but it's just the point that I compiled, like as I said, there are like 80 projects and fuzzing and whatever, millions lines of code, and then I received this. This is like complete test case for reproduction. How many? 5 lines, and it somehow breaks. So I had to fix this. And of course, again, as I mentioned, sometimes you have to claim that you are GCC, and then you either implement some GCC extension for some project to be compiled, or sometimes the projects actually try to do some fallback, but this fallback is never tested. So I can try to compile a project, and actually they will have bugs in their fallback code because they have never even properly tested it because they compiled with GCC. So you can. This is also kind of a problem. Until I can claim that I am fully GCC compliant, I have to face such things sometimes, even though it's getting better and better because I implement more and more compatibility.
Wow. Yeah, it was ugly.
I mean, that problem's not limited to C. There's plenty of databases that have decided to just implement pieces of what Postgres does that's not in the SQL spec because so many people use Postgres and they can't switch to your database if you didn't do the thing they did.
Yeah, sure. I'm not claiming this is like unique problem, so to say. It just in this particular example, I was just mostly talking about that they actually some people try to implement some fallbacks, but those fallbacks almost never get tested. So I would say it's probably better to just fail at some point for the program to compile to some error preprocessor directive, because these fallbacks are often not very functional. And spend quite. Yes.
Better to fail than to get a buggy output that then you have to go debug and the developer complains your compiler's crap and all that, as opposed to just saying no, I don't support this extension, whatever. Go be GCC. I get it.
Do you have a way to turn off the extensions? Like sometimes I want to be like, okay, I want this to compile on non-GCC compilers, so I want to know if I'm using some piece of code that's not going to work and it's not standard.
Well,
so,
if
you have a way to turn it off?
Developer, you just grab a non-GCC compiler, but they're not doing that, right?
I mean,
they're using GCC, and they say, well, if they don't have a GCC, we'll have to do something.
Well, like sometimes I'm on a platform, right? Like let's say I'm on Linux, and there's not a lot of like if I run Clang, most of those GCC extensions are enabled, right? So it's kind of hard to like I want standard C, and I want to know if my program is using something that it shouldn't be, so that like if on a different machine I tried to compile it using a different compiler, then it would fail. But maybe I don't have that on this particular machine, so I just want to turn them off.
So for my compiler, initially I implemented just the standard, and initially I tried to keep a flag for each feature on top of the standard. But I arrived at the point where it gets quite hard to actually reason about these things. So I abandoned this, and at the moment I'm mostly in GCC mode always. I still have some of these flags. They are not comprehensive, but keeping every such feature behind the flag is quite
a lot of
flags.
Well, what about us?
Pedantic mode's a hard feature.
Just like one flag that's like you have stuff that's not in the standard, or you do have it.
Like C compliance.
Yeah,
like C compliance.
Like,
I understand. Yes, the point is it's still not easy, and I myself wouldn't test it much because I compile mostly software that uses these extensions. So most of my test suite would not compile with this pedantic flag. So in a sense, I would again fall in the same trap that I have some feature which I'm not testing. And I believe it's not productive, not faithful, I would say. So at the moment, I maximize compatibility with real software, even if it's not fully standard compliant.
So as you said, you're leaning towards GCC. What about Clang? So do you try to be the superset of both, or mostly GCC on the?
I implement some of the extensions that Clang supports, mostly atomics, because Clang had some different built-ins for atomics. They share most of the built-ins and extensions which are of interest anyway.
Mm-hmm. Mm-hmm.
For Clang, again, because I support FreeBSD, OpenBSD, other BSD systems, some of those use Clang as system compiler, and their standard libraries rely on some of those Clang built-ins. So I do implement them, but again, it's not like I do not keep full documentation of everything, every built-in, every configuration, so to say.
But do you try to keep them separate? So on the left are the GCC specific stuff, on the right is the Clang specific stuff. So you can track them where it came.
It's basically superset of whatever I need to have implemented. As I said, it's doable, but it would take actually more time to keep this all tested and reliable. And I initially tried to have some flags and some like very fine grained flags and then pedantic kind of high level flag, but I arrived at the point where it's quite a lot of effort to keep it all working up to date and be sure about it. So at the moment it's just GCC plus Clang extensions mode always on.
Your goal is to just compile the C code no matter what it requires, either GCC or Clang.
Basically, yes. I have like some real world projects, which I listed some of them on the previous slides. But like, if I need to compile Python or Postgres, I need to implement whatever Python or Postgres rely onto.
Yeah.
So that's basically the goal. Yes.
Sure.
And then, for now, I will proceed to the last part. Actually, what I learned firstly, I learned that actually the time travel debugging is very, very useful for this kind of development. And I'm not sure how actually many people use such kind of debuggers. But I always kind of now promote this approach and find it very useful. I use this reverse replay and reverse, how it's called, record and replay framework, RR project, which relies on GDB, and especially for all kinds of compiler bugs. What I actually do when I find a compiler bug, I record this execution, I put some watch point when the fault happens, and they reverse continue back and back in steps until I arrive at somewhere where it failed, actually. So to me, it's very, very useful tool, and I actually always try to promote it, or this approach, so to say, to debugging. And also, it's very kind of often it's useful to do side-by-side differentiation debugging with this tool against something compiled by GCC or Clang, which you assume is correct, and then you at some point you just arrive at divergence, and time traveling is very nice to have.
Yeah, I didn't have that when I was doing C2. It would have been nice.
Yeah, I was going to say, my opinion on time travel debugging has changed. When I first encountered it, I was like, this is ridiculous. It needs a couple of gigs of RAM. And now I'm like, this is awesome. It only needs a couple of gigs of RAM.
Uh-huh.
I mean, it's indeed awesome, because I would say that I would have not finished the project to the current state, brought it to the current state, if I didn't have these two, probably. There were some bugs which I was not able to approach otherwise than just by recording and then stepping back. Or it could have taken like weeks, probably. With this tool, I resolve things in like hours or days at most. So I recommend it basically to everybody, always. It's a bit, it's not always easy to get it reproduced, especially in multi-threaded setting, but as long as you can reproduce the bug, it's very nice to use. And then some subjective lessons about the architecture. And I already mentioned that I have multiple intermediate representations. So my kind of idea and why I didn't want to implement everything correct, not to say correctly, but comprehensively, have SSA all the way through and everything is nice and classical. In that sense, I started with the threaded code, because to me it was very important to get the first version running and compiling the real code. And therefore I could debug it completely for the whole translator and make sure that it works. So from a compiler evolution perspective, I would say that I would first go for that, implementing the pipeline to the point where I can run everything, and only then ensure that it's performant and nice and good. But again, it's constraint of my like solo development of this compiler. For teams, it's probably different. And then again, I mentioned that I have this quite comprehensive test suite of 80 software projects, fuzzing and bootstraps, and actually it's again indispensable, so to say. I wouldn't be able to make sure that the compiler is working and correct unless I had this test suite, which I run nowadays like nightly. Each nightly build is like 15 hours of tests, and only then I can basically make sure that it's actually working to some extent, that I can be confident in it. But it's very, very important.
Yeah, I'll 100% that one.
And this is the third part is again how I structured my pipeline. As I mentioned, first I did this threaded code generator, made sure that it works. This is kind of first lowering boundary I had. Then I did high-level SSA, made sure that it works, expanded this suite. Then I improved on this virtual assembly, and finally I'm doing the final step of lowering, constructing SSA for target instruction set. And to me, this lowering is natural path of evolution in the compiler. Of course, as I said, if you have like founding and team, you can probably be more be of like larger scale, so to say, and do everything at once, have nice classical pipeline SSA everywhere. But as a solo developer, to me, it's very important to have this very structured approach to development, where I structure the pipeline and get it working at each step.
So each IR translation is a whole pass through in the compiler.
I mean, what I meant is just, let's say, first, initially, I had this stack IR shown here.
Yeah.
Implemented the code generator for it as it was, threaded code. I made sure that it works. I made sure that it compiles code, and it was already like complete C compiler working. And I could do it before I proceeded with SSA, with instruction selection, with whatever. So to me, it's kind of natural boundary of evolution in the project. Then I did this SSA. Here, once I was satisfied with threaded code, how it works in the pipeline.
Oh, you mean that it's an iteration over your approach, not different IRs through the compiler pipeline?
No, I'm hearing him say
these are different IRs through the compiler pipeline, but they were kind of a result of the iteration. So they did not appear. They did not appear because because this was my architectural idea. They appeared because that was how I approached the development over these 5 years, actually. So, but they do still exist, each of them. So they are present in the compiler.
And my question: when you're translating between IRs, you do a whole pass, because I'm assuming the IRs are not compatible with each other, or they are somehow backwards compatible, let's say, so you can still use the next representation, the earlier representation in the next IR.
So they share semantics pairwise. So if I go back here to the stack-based representation, this one, and the SSA shares semantics in terms of the opcodes, except for some special opcodes. Like SSA has FICE, stack representation has stack management, but all the rest is shared. So the construction is quite straightforward. But the same goes for this.
Walk the one flavor and produce out the next flavor, however many times it takes to go through the compiler. That is, say you walk everything in the stack version and produce the puddles of SSA version.
Yeah.
Is that's what I'm hearing? That's what I'm hearing Theodore ask.
That's my question. Yeah. Do you do whole pass, or you kind of step on each other?
Is it incremental? Is it incremental?
Okay, that's the right word.
I was the stack, now I'm puddles of IR.
Yeah. How do you bridge that?
By bridging, I mean, I just have constructor pass, which is fed with stack IR, and it produces these puddle of nodes SSA, and actually
it is a whole pass to change from one IR to the next.
Yes. Yeah. Is this correct?
Yes, basically it changes the shape. As I said, the opcodes stay mostly the same, and it also shares the other structures. Like, as I said, the stack-based IR is not only execution part; it also defines all the data abstractions, the function abstractions. These stay the same between these two IRs. So this puddle of nodes is actually kind of a flavor, kind of thing of top of stack IR, which reshapes it into something friendlier to the generation, to the optimization. Then for the virtual assembly, this is already quite close to the target architecture, to x86, and again, pairwise, it's very much corresponds to this target SSA, which I'm working on now. So again, they share the abstraction level, but they have different shape. So to me, it's, again, as I said, it's kind of natural boundary of evolution of compiler when I implement something which is kind of executable on some executable abstraction, and then later on, next year or sometime, I put something analytical on top of that to perform optimizations and analysis. That's what I meant here. So to me, these IR boundaries are development milestones. And kind of my final subjective lesson is actually it's not necessary to write C compilers. I enjoy this practice, but I don't recommend to anybody. I would say because it's not really a pleasant language to work with.
Is your compiler written in C?
Yes, of course.
Self-hosted.
It bootstraps.
Yeah. Okay. Yeah, there's
It
some things I
compiles.
like
You
about
mean
C++.
it compiles itself?
Yeah, it's self-hosted.
It compiles itself. The bootstrap is bit precise, so it actually produces something which is identical to the next previous station, so forth.
Yeah.
And as I mentioned, it also produces like this portable bootstrap where it compiles itself. It compiles muscle standard library, binutils, and a couple of other libraries, and does so 3 times to make sure that it's actually not only like self-hosting as a compiler, but it can self-host a whole development toolchain.
Yeah, it's a pretty impressive piece of work.
And actually, this is my kind of final slide. And I actually wanted to make an announcement. It's a bit of coincidence. I did not plan so, but today is actually exactly 5 years since I started development of the compiler, like day to day, 5th of December.
Congratulations of some kind.
Congratulations.
Yeah,
I was expecting this project to be much older based on how much it sounds like you've done.
Yeah, I know. Right. Especially if it's a one-person job. There's a huge amount of things done. Yeah. Congratulations for sure.
Yeah.
Thank you.
You should be proud.
I thought you said something about you were trying to get into a PhD program.
I am doing a PhD, but on different topic in software verification.
Where? What school?
So, but basically this is it. So if there are any questions.
What school are you getting your PhD at?
What school?
Yeah, what school?
What school? It's in Estonia, in Tartu University.
Okay. Nice.
Okay, questions?
Yeah. Don't know what to do with that one.
In retrospect, would you say that you need the stack IR, or would you go straight to SSA-based IR with register-based IR instead?
I would say stack IR is no. I mean, it's nice to generate from the translator. It's very natural to generate. I would say perhaps to me it's kind of more natural than the register IR. So I kind of plan, even in retrospect, I would say I plan the IRs in a way that it's easy to target from the previous layer. So I would say yes, I would still do it.
Interesting. How about targeting the next layer after that? Isn't this a bit of an overhead, at least if you need to go to the machine code in the end, or is it not that much of a problem in your experience?
I mean, there's indeed overhead, and one of the problems of the compiler, it's the compiler itself is not very efficient as a piece of software itself. So it's a bit slow and it consumes memory. Some of this is because of these abstractions. The abstractions themselves are not inherently slow, but just it's quite a lot to manage. So
In a ballpark, a comparison to say GCC, it takes you twice as long to compile, or?
it depends. I do not even measure because my goal is not beating GCC in any ways. Like it's unreasonable. I know that it can be slower, yes, but as long as it compiles in a reasonable time and produces reasonable code, that's kind of my goal at the moment. So
I would say it's not a race, but 2 times slower is different than 1,000 times slower.
Oh, it's not 1,000 times for sure.
Okay.
But you think it's on the same order of magnitude as GCC in terms of speed? It's roughly the same speed as GCC. A little slower, a little faster, depends.
I mean, it depends. It's also in terms of memory consumption. I'm not very efficient in the compiler itself. but this mostly is my philosophy is that I get it working, and unless it's somehow too ridiculous in terms of like memory consumption or time compilation time, it's fine. So it's slower, yes, but I only optimize when it gets problematic, actually.
I find in a one-person project, optimizing for simplicity tends to be much more important than many other goals.
Yeah. I'll agree with that one. So you have Dwarf going, you can debug with the GDB. You have enough Dwarf?
Yes, it produces debug information. It's actually a very important step also in the compiler development, because once I have debug information, it's much easier to debug what bugs in my compiler itself.
Right.
Because otherwise something fails. I compile Postgres, I try to run test suite, it fails somewhere with segfault, and then if I have debug information, I can at least make sure that I see what's around. Otherwise, I have to correlate with the original code and guess and such, and it's not trivial.
Are you using Dwarf for that or some other?
Dwarf. Version 5.
Because I've heard some stories of people bouncing off Dwarf where they try to implement it and it's just a lot.
Yes, it's a lot, and it's not. I mean, it's not very friendly, so to say, to the implementer. You have to think about it, and you have to separate your debug information into multiple sections, and then you either like produce some internal representation for your debug information, and then unroll it into these sections with some cross references. In my case, I avoided doing this, so I do kind of multipass generation, where I generate information for each section sequentially and keep some cross references in memory and put them where appropriate. But I kind of, yes, I do understand why people wouldn't like to work with it. It's very, I would even say unnatural. But at the same time, it's probably efficient in terms of storage, because it deduplicates a lot, and you can store your debug information very efficiently if you care.
That was a C2 compiler experience. Was the debug info for Hotspot was quite voluminous. It was often bigger than the generated code, often by a fair amount. And I spent some time compressing it, figuring out how to compress it, what was the common patterns, Huffman encode this and that, because it was only ever unpacked if somebody actually stopped in a debugger, but you generated it every time. So yeah, you had to do something about size of the debug info.
I wonder if all the tricks people use for columnar stores would work for debug info.
It wasn't as regular as that. I didn't have columns. There's definitely highly repeatable patterns. Many things were null and known ahead of time. There's always a shortcut for null. Many things were, there were some small constants other than null, but not tons. There were a lot of constant pointers, so you wanted to gather them up somehow and share them with the runtime. You know, everyone who ever did a static global of anything of any kind had a pointer. And the generated code had the pointer, and the debug info had to have the pointer, and you actually didn't want to have it in several places. So there was a bunch of sharing that went on there. I'm trying to remember all the things I did. At some point, I kept a giant corpus where I compiled 100,000 functions and looked at their debug info at every save point, and then try to optimize the representation based on that. I think I still have that data set.
So having implemented so much of the C spec, what are the fiddliest bits that you had to come back to multiple times because you thought you had them right and then there were some subtle nuance?
I mean, overall, I would say C standard is not well phrased, especially with the newest additions, as if it's like a lot of patches to the text, and it's not, I would say, coherent as a piece of text. Sometimes it's very general comment, of course, but you read the standard, then you go look at what GCC C-Lang does, then you go perhaps even try to read their source code, and that's a lot. And the most problematic one was actually not probably with the standard. I had a lot of problems trying to implement correct allocation for bit fields. It took me probably a couple of weeks to get it right, and I ended up having to read again Clang source code to actually know the exact algorithm is much simpler than I thought. But of course, the standard does not prescribe it. The ABI document did not prescribe it, and you could not infer it from just looking at the compiler outputs. So this was quite tricky to get right.
This is something I actually agree with a lot with C and C++ and OpenMP experience. And I think the only solution is that we should get over this and do what hardware industry has been doing for decades, which is actually formal verification and formal mechanized standards that computers can understand. Because informal English prose, like the ISO C++ documents or C, that's not really a standard. That's just informal English prose. And that's always going to require wise men or women who interpret what the poet had in mind. So
It's not
as
really.
long as it's not formal, I don't think it's going to be a fixed problem.
Yes, I know a lot of people who think the next great computer programming language will be English, and the LLM will just make the binary that does what your English said. And I was like, if you've ever tried to write or read a specification, programming languages are actually pretty good at being explicit.
Do it on me, not what I said. Yeah. Sorry, Ryan, you were going to say something?
No, I'm good.
Don't have to if you don't want to.
Well, I find the Q&A form pretty good. So this is how I do the LLM prompting, and it gets me reasonably good results.
Go back and forth with the Q&A and
Yeah.
yeah.
But I'm not
I think
sure.
the complaint here was that the C standard over time is still prose that's being patched, and therefore it's difficult to understand and difficult to manipulate or verify that you got something right out of it. Which I don't think that Q&A with an LLM is a good answer for that one.
No, it's got too much subtlety there. It works for simple things like web apps.
So what would
Or to
you
come
do?
to a single answer. There's a lot of interpretations that's like both interpretations are totally valid, but it's really nice if your compiler interprets this thing consistently everywhere.
Well, that's what you have to say.
What would you do about like undefined behaviors though, for example, in like a formal specification? How would you like properly model that and like implementation defined? Because I guess you could,
Implementation
but
defined is easy because it's basically like C++ templates. You have to parameterize your specification of all of the implementation details that you're going to then get filled in. Undefined behavior is a cheeky answer is not defined. So you don't define it.
So I would claim that
It's
you should
not
have
as
undefined
much of a
behavior.
cheeky, because if you think about how LLVMIR is being formalized in the Alive2 project, which does translation validation, they don't exactly specify this either, but they do specify things like you cannot introduce undefined behavior when you have an optimization pass. So, for example, you can rewrite poison to a lot of things, but you cannot refine a lot of things to poison. So you cannot change a scalar to a poison. So there is basically the question is that you are only allowed to do behavior refinement. You are not allowed to introduce undefined behaviors as a compiler. But that doesn't mean that the specification has to be deterministic. That's the difference actually between the equivalence, the behavior equivalence, and the behavior refinement. So in C and C++ compilers actually cannot in general be equivalence preserving, because you may be allowed to have infinite set of behaviors, but you may be able to pick one, and that's refinement. So that's basically the difference. When you want to probably prove something like a C compiler, you can only do refinement proof. You cannot do equivalence preservation proof.
I'm still in the zone of just if the language has an undefined behavior built into the spec, you define an implementation and everyone just lives with that and move forward. Put it in the spec and just move forward. No
so
more undefined behaviors.
I'm wondering though, like if how easy it would be to like mechanically prove that, you know, a transformation the compiler is doing follows like this spec, and or like if something can introduce undefined behavior, how would you like prove that the transformations are correct?
Well, if
That
it
seems
introduces
difficult.
undefined behavior, I say it's not correct.
So that's done by a Light 2 product for LLVM IR transformation. It's actually pretty good because it can reasonably control flow graph changes. So even passages like that to simplify CFG. And then on top of that, you can do peepholes. So it can actually reason about that being correct or not. So you have to encode all of the semantics of LLVM IR instructions. And then, so that's basically one example. Then this is a very, very, very simple example. You have the source, which is the unsigned division, and you have the target, which is the left shift. You can see that you are dividing by 8192, and that's equivalent to the shift by 13. And if you change this 13 to, say, 12, you can see it's going to complain about it. So you can try breaking this diff if that's it. And now you see that you have a value mismatch, and then it's going to show you an example value. What is the source? What is the target? And those values are different. Hence, you have not refined the behavior. Hence, the optimization is incorrect.
But like if you have this and you have a function that has like 8 or 10 different inputs, what if there's only like a very small set of the inputs that cause it to break?
It has to find that one input, but notice that this is true about optimizations themselves. So if you don't know anything about compile time, if you only know at runtime, then you can't do optimization either, right? I don't know if I understood the question correctly, but if you are talking about this 13 being a compile time constant, yes, but that's also the case for optimization. To do this rewrite, the compiler has to know the constant as well.
Mm.
So is this tool just exploring the integer space for mismatches? Like
That's a
are
bit
is there
more.
some
The authors have also done the validation for the backend, AR64 backend. I'm not sure if it's publicly available on this one.
I guess I'm asking, is this tool discovering the error via some sort of guess and test of different inputs? Or is this tool doing semantic analysis to decide
Quick
that by the
analysis. And I have just posted the paper that does the backend as well, translation validation for LLVM's AR64 backend.
Oh, okay. It's like a giant PDF here. Oh God, it's a vast PDF. All right, well, I'm not gonna go share this. It'll take forever.
And that's one fairly involved because that's actually also has to look at the assembly instructions in AR64.
Right.
If you look at figure 1 in that paper, that's kind of giving
All right.
you an idea.
Hang on, let me get the share button. This guy.
So they built on top of this infrastructure, and they have an interesting approach when they basically in one step, then they lower the LLVM IR using the AR64 backend, and that's the regular normal compilation using normal LLVM backend. But then in addition, they leave this machine code back to LLVM IR. And now notice you have two pieces of LLVM IR. So now you have reduced the problem of trying to compare whether this is a refinement in the LLVM IR space. And if not, then that means something has broken along the way. So now you can also use this infrastructure to verify the backend compiler, which is kind of neat.
Yeah, no, that's a bigger piece of work. I wasn't sure they were going that route or not, but yeah, sure. All right, I'm gonna stop looking. Make sure let's get it in the docs, but that's something to be read offline. Where's
I'm
my
not sure you'll be able to verify mid-state because let's say a CF nodes will do many transformation. How do you verify that the code is correct if you're not generating all the way to see that it's still correct? So intermediate verifications of the correctness, let's say for the graph, would be a hard thing.
Well, as long as you have semantics for the IR, that's all you need.
I am doing visual, it's peephole transformation. So the transformations are individually very small. And then I do visual, investigation that I did the transformation correctly. That being said, it's not formal. I get a bigger transformation. I don't get it correct. And then, something breaks. The usual story though is I don't get an incorrect transformation. The usual story is I don't collect the required neighborhood boundary and I miss an opportunity, and then the
But
assorts catch me, like you failed to recognize that you could do this particular people because the prior people didn't announce that he changed something that this one cares about.
and the order of transformation is non-deterministic.
It's not
If it's
deterministic.
so
Yes,
that would
incremental.
it's
It's the
incremental,
algorithm
yeah,
is just
but no.
incremental, and then you don't necessarily get the edges of the incremental correct
So yeah,
reliably, and so you miss something. And the assorts catch me pretty quick on that one.
yeah. So
This
in order to test for correctness, you have to play each transformation, each possible combination of transformation to be
In
confident.
theory, in practice, I sample. I pick a random seed for the work list and I run it.
We're back on the. Do you
this
are you able to do a verification like that, like Matt shows? But I'm not confident that it's really feasible.
I-
this is really similar to quickcheck. I don't know if you guys have ever used quickcheck. That's the, I mean, it comes out of the Haskell world, but then it spun out into various libraries like hypothesis in
What's it do?
Python or
I
system.
usually just hear it as generative testing.
Yeah, the generative testing, but it's like the property-based testing. And then there's an extension of that, that the guy who created quickcheck switched to using Erlang from Haskell, and then he created this company called Kuvik, which wasn't very successful. But I watched a talk that they did, and it was really good, where they talked about testing complex systems, and the example that they gave was testing the CAN bus of like a Volvo. And the way that they tested was they create a model of the system, and then they run the model of the system and the system in parallel with each other, and then just verify that they produce the same results. But the thing is that if you've got a system with optional steps, which is basically what every transformation is, then I think that you can just achieve the same thing by disabling steps randomly, and then you can basically systematically test.
Can I do that too? Right.
Because then you just need to have some way of saying that the output is the same, and then especially if you can randomize the programs that you're testing in some way, or maybe you have a large corpus would be fine for
Well, okay, so
programs.
I'm doing fuzzing, and then I'm doing random seeds for the workless poll, so the peepholes will run in any order. I could, in theory, have something that tried turning off one class or kind of peephole and running again. And then I check for, I hit that same fixed point at the end. So I have a way to say these two program IRs are the same modulo various renamings. Um, that's the current level of testing I'm doing. There's nothing formal about it in that sense, but it's sort of statistical engineering statistics say I would have hit it if it was reasonable to hit it.
Yeah.
Would love to have something more formal. I'm not certain where you would go with that.
Do you have sort of a big epic of I'm going to do all the high level peepholes, and then once those things have stabilized, now I'm going to do low level peepholes? So, like in the thing we were talking about today, you've got four different IRs. There's a clear, I have to finish the first one before I start the second one. I feel like in a sea of nodes, you might have some things that lower it all the way down while other things are still pretty high level.
I have that strictly at calls, whether they inline or not. And then in order to get that final output the same, so what I was calling the one-step church roster property, it doesn't matter what order you do, the people should get the same answer. The inlining decisions have to be the same no matter what order they're applied. And so I'm likely to cheat on that one. I have some inlining decisions that are really lame right now. So it's similar to where Eugene here was saying, I do something with inlining. And what I really said is if it's trivial and obvious, then I inline. And if not, then I don't. But there's a lot of opportunities I should be inlining. And I'm just not right now because that's the state of the project. Fine. As soon as you get to a point where you have more complex heuristics that say I want to inline or not, then it matters what order you do the inlining because one inlining decision can drive out or turn on or off another inlining decision. And if you want to claim that you're going to hit the identical output every time, you have to have those, inlining decisions always or never kind of happen. And so that turns into how do I recognize that the inlining decision is the same either way? My current plan is I'll run all the things that are not inlining down till I'm stable, and then I'll go back and pick the one best person to inline based on whatever heuristic. But because I have the one-step Church-Rosser property, when the peepholes are all done and the IR has been optimized as much as it's going to be so far, um, there'll always be the same one best next inlining decision. So I'll be deterministic there as well and do that inlining and then settle it out and then make the next inlining decision and settle it out. Repeat till you're done. So there is a way to make it deterministic, but I lose the property that it's random on the work list, at least for the inlining decisions that depend on each other. And anything that's code growth has this problem. So actually, unrolling has the same problem. If I have a loop and I decide I want to unroll, it makes the code bigger. You make a decision about inlining or not based on size of code. So you unroll first. You don't inline that function because the body's big. Maybe you're better off inlining first and then unrolling. So now you have to make a decision about how you do those in what order if they're going to play off each other. Well, and you want to be deterministic. You want to get bit identical. What Eugene said. I've done that before too with compilers. You want the output to be bit identical because it's a fantastic way to verify that you got something correct. Any source of randomness needs to beat itself out pretty quick, or you will be, in a hurting way with random bits. Hey, are these good bits or bad bits? Fine. So
Is
yeah, I
there
don't know
a
where we ended up
is
with
there
that.
an option to, I'm not sure if this would test anything, but just basically disable some peeps, run the compilation, and then after it's settled, then re-enable the disabled peeps and
Hmm.
ensure that it now. So basically, maybe you're only
You're
forcing like it's
you're
particularly
forcing the
poor
work list
ordering.
order.
What's that?
You're forcing the work list order.
Yeah, you're forcing the work list order, but you're forcing maybe like especially bad ones in a way. I don't
Yeah,
know.
right. No, I think that's a reasonable thing to do. I don't have the infrastructure set up for that. It wouldn't be hard. It would
Yeah.
just be if this peephole was enabled or possible, you throw it on a to-do later list and finish the main work list off and then hit the to-do later list.
Yeah, right. Yeah, you actually have the infrastructure if you have the multi-work list thing. So AA has this. You just have to shift it into a later work list.
Right, right.
Yeah. I don't know if it would test much though.
Well, that was my theory was I'd just pick in random, not a huge count, but pick some random count of of seeds for the work list. So the work list draw order varies, and then I get an answer, and then I
Yeah.
reset and draw again and get another answer, and then I see the answers are the same and declare victory and move on.
Yeah.
Um, I think in the AA I settled on four, but I had a knob I would dial. In fact, I dial that knob up occasionally, and would find more rare conditions. Like I set the knob to 1,000 tries, so basically 1,000 recompiles, and
Okay.
verify that I got the same answer out. So yeah, it's a thing. Although I think fuzzing got me a very similar effect in terms of the class of bugs you would find. What do we have here? It's only 11:20. So what else here? Other things. Um, better the register allocator that I mentioned earlier. I think would be fairly straightforward to port to C for a C compiler compilation. I cleaned up the one in Hotspot by a lot. I redid from scratch, and it's a hugely simpler thing, and it gives you a graph calling register allocator. So it does a reasonable job on bigger programs.
Anyone trying the advent of code this year?
Oh, the advent of code. You're very soft again, Cameron. It's you and your however your mic setup is. I haven't looked at
Yeah,
the advent of. Is it coming around?
I could probably do it this way, but yeah, advent of code. Anyone doing it this year?
Oh God, I looked at it earlier in the season and haven't looked back. Here, let me go see what they're doing here. No, I'm like hacking new job and I want to hack simple and I've been forever. Here it says 2025. Um, about when's the calendar on the thing? Here's the calendar. No, that's not helpful. All right, it's not up, is it? They haven't started, have they?
I think they're on day 6.
Yeah,
I'm looking
it started.
for, I'm at the 2025 version. They haven't put the
I
next
put
one
the
up.
link in the chat.
Oh, they're on day
Ah,
5. Day
okay.
6 comes up in 10 hours, I guess.
Mhm.
Huh.
I was planning to try some of them, but I've been busy in a debugger.
Huh. Okay. I'm looking at the LLVM bit hacking thing. I do some known bit propagation things. Nothing, I want to say, strongly well-defined or formal or anything. Just ands and or masks that wipe out bits.
Hmm.
Go in the type thing. Yeah. And advent of code always looks fun, and I never have time.
Same. Yevgeny, that's pretty impressive stuff.
Thank you.
Uh,
If you want to slow down your progress, you need some more help. Get a couple
yes.
more people on the team.
Hmm. What? Oh, I see. Does claim there are almost only 5 tests this go around. I'll steer. Never mind. I got come looking at the Advent of Code webpage. I'm like, oh, well, I want to play. No, stop. Uh,
Yeah, get Aaron to put the AA entry in for you.
boy, you're still hard to hear. Say it again.
I said get Aaron to put the AA entry in for you.
There you go. I don't have it far enough along. I switched to simple to get the end-to-end thing going. I have some really cool type theory discoveries that I want to implement in a language that hasn't happened yet. And simple has stuck me doing modules, which has actually been making slow progress because new job.
Maybe you can
Um,
get Tommy to do the simple one for you.
yeah, when the modules land, I'll have the standard lib, simple standard lib, not in the same compilation unit as everything else, which is what it is now, which sucks. Because you're compiling the entire standard lib to compile hello world. That's not helpful. So when that hits, then I think I'll be at a point where it'd be reasonable to try writing bigger projects and see if I can get something going that was worth doing something with. Whether it was and maybe writing an advent of code thing. I've found some website with a bunch of small, modest programs that did something sensible, like read ASCII text for a list of numbers and then bubble sort them and then write them out. So you had to do some IO and some parsing.
Right?
And I implemented those in simple and pretty straightforwardly. They work nicely. Um, but I need to get my module story done. And that has been tied up with constructor syntax. Uh, the conflict of you can literally write one line of code that does something useful, and that's a valid line of code, like a one-line program that's short and simple, sys.io.print hello world, as a for instance. And
Hmm.
also have like classes and instances set up for subclassing at some future date. So that you don't have to start out by saying package, com.cliffc.c of nodes dot blah blah blah, public class, main or hello world, open curly, void main, open close paren, and system.out.println hello world, whatever. The minimal Java hello world program is like 8 lines or something stupid. I was trying to ditch all the extra lines So that means that when you open a file and start parsing and running, you're immediately in a class definition. The class definition is the name of the file. And that meant that I had to start by not just parsing text, but by building up a class structure hierarchy that was going to turn out to show up in the files in the module system for linking and all that. You got that just for free because you opened a file and put some code in it. And then there's other classes, and you can refer to class, this class to that class via path hierarchies within projects and stuff like that. So all the things that you would do to go find one thing or another thing that Java does with packages imports, C folks do with pound includes. That's all what I've been doing on the last couple weeks. Well, if we're going to be done, we can be done.
By the way, I'm just going to end with a plug for a very good podcast I have found. It's by Aaron Stamp. It's called Iowa Type Theory Commute Podcast. I think he started this in like 2019,
Iowa,
but it's still going.
Wow.
And he has an entire chapter on module systems, which is actually pretty interesting. He goes through a lot of languages, also including Haskell, Standard NL, Agda, a bunch of newer papers. It's pretty interesting. Modula 2. So let me just plug this as a pretty good podcast. It covers a lot of topics that are usually not covered in other, I have found.
Iowa type theory. That's hysterical. I have never heard of this. And the guys have been obviously going on for a long time. So you have a transcript on these things? I'm much faster reading than listening.
No, I do listen at the speed up.
Yeah, I don't do long distance driving much anymore, so I don't have a podcast is what I would do in a car while I'm driving. Fine. Interesting. Yeah, I'm kind of faking my way to a module system, and somebody should tell me I'm doing it stupid before I get too far on. But I don't think I'm that out of line with it.
Yeah, why don't you present it next week?
I thought I tried last a couple weeks ago. I could try again. I don't have any. I could try. I'd have to put together slides because it helps me to have a visual thing. Instead, I have a set of goals, and I've mostly got the goals met. And I haven't played with it in any large scale way, so I have no idea if it's worth anything. And we talked about this before, Cameron. It's just like there's a root to the project. A module is a project. That I wasn't going to split. So one module can talk to another one, but there's like different projects or different directory roots or whatever. And if you talk to a different module system, you have to, full path your way. And of course, there's a way to make a short name for the long name. And otherwise, within the module, you just hunt relative to files within a module, which are files in a directory. I could bring it up next time and see what happens here. Like I said, I think I talked about it a couple weeks ago with you, and I went back and forth with you on some of the ideas, and I mostly picked things that you were doing or cherry picked around similar like stuff. The end goal being,
I thought you might have some new progress on it. That's what.
Oh, I could say progress. Mostly the progress was restructuring how I did my constructors. Because I have a class constructor. When you start a file, you're writing in the class constructor on that file just immediately. That's just what that is. And then once you start a class definition, you're in the instance constructor to make instances out of that object of that type. And I was just trying to sort out how finals happen and a bunch of other things. So that they're mostly settled. So I bring it up next time. Let's do that next time.
Cool.
And yeah. And I don't think there's anything else going on next week. I'll go confirm I'm not like crazy here. God, another. Right. Okay. Yeah. Next week I'll have something to say. I don't know what, but I'll say something.
I'll try to have my Zoom working. Good.
Well, I just can't hear you.
I said I'll try to have my Zoom working.
Yes, or learn how to shout, or eat your mic or something. Okay, so let's just go call it done early because I think we're at a good stopping point. And, quality over quantity, and we'll just meet again next week. All right. Bye-bye, everybody.
Bye.